Hello and welcome back. 4.5 linear approximations. It's that time of the year, you know. Yeah. I know Mercedes already started advertising their cars that should be purchased for Christmas. So there you go. We all know. Linear approximations and differentials. How much is ln of 3? Yeah, exactly what I thought. How about square root of 15.2? Oh, you're reaching for your lane calculators, I see. But let's paint the picture. What happens if you are on a desert island? The batteries in your calculators and your cell phones ran out. Wilson is gone too. There's absolutely nothing else to do. You want to build a hut. You need to figure out how much is ln of 3. What do you do?
Question?
Yes.
Why do we need to know the natural log of 3 to build a hut?
Trust me, been there, done that, so you need it. Also the square root of 15.2. Yeah. They all work in. So with this particular section, we're going to learn how to approximate values to the great precision, though. And you can use this to annoy others, obviously, when they say, what do you know? I know how to find ln3 without a calculator. What do you know? Right back into their court, right? Planning on using that later today. It's going to be awesome. So let's see what's happening with this linear approximation business. So first of all, this linear approximation, I'm just going to point the arrow like this and say tangent line. And technically I'm done, all right? Because what we are going to do is we are going to find the tangent line at the near point, which we can easily compute. And then we see that the number that you actually need to compute will have the same y value, or pretty much the same y value as the tangent line y value. I just said too many words without the picture, so nothing makes sense. I understand. There you go. So here is some function f of x. Could be the square root, could be ln, could be whatever. It doesn't really matter. What matters is that you want to compute a value here, value at c. But you know how to compute a value here at a. That's the one you know how to compute. So you find the tangent line at a because that's what you can compute. And then instead of computing c on a function, that was annoying, remember? You compute c in a tangent line. And guys, tangent line computations are just a linear line, right? So simple addition, multiplication, and so on. So if you are to compute, to try to find what is this y value here, look, I'll zoom in. You see that the y value on the tangent line is pretty much the same number. Well, it's not the same, obviously, but it's close. So this is what we are doing with this section. So without too much, let's find blubbering, I guess. Let's find the square root of 15.2 because we can. No calculator. We do it the NGIT style. Oh, some of you are transferring there? Awesome. You'll need this. So let's take a look. I know that I can compute square root of 16, which is 4. So I will find the tangent line at x equals 16. So your job is to find the closest possible point that you can compute without the calculator. So for, let's say, you want to compute ln3, what would be the value that you can compute without a calculator? Ln e, right? So e. So you will find the tangent line at e. Because ln e is 1, that's easy computation. So what we do is we find the tangent line at the closest point that we can compute without a calculator. From 15.2, 16 is the closest because other values are 9 and then, I don't know, 121, right? So let's see. Tangent line. Well, what's the function? Function is clearly square root of x. That's the function because you are computing square root of a number. That's square root x. How do we find tangent line? Anyone? Thank you. We find the derivative. And then when we compute that derivative at the point, when we compute that derivative at 16 in this case, 1 over 2 times square root of 16, we get 1 over 8. And that's the slope. That's the slope m. So now I have a tangent line. We have the slope, we have the x value, we need to compute y. So what do I have? I have a point 16, 4, and I have slope is 1 over 8. So I can compute a tangent line easily. Y equal mx plus b. We have y, which is 4. We have slope, which is 1, 8. We have x, which is 16, plus b. That's b is 2, right? So the tangent line is y equals 1 over 8x plus 2. That's what the tangent line is. So square root of 15.2 is approximated by computing the tangent line at 15.2. I hope this makes sense. So all I need to do now is, since I'm on a desert island, I have a stick, I have a sand, right? I can do this division by 8 without a calculator and then just add 2 at the end. So 8 in 15 goes exactly, once. And then in 72 goes 9, so 1.9. And then we have plus 2, gives me 3.9. This good? Now we're going to use the abacus and figure out what we have. So what is the value that calculator would say for square root of 15.2? 3 point, give me 4 decimals. That's 3 decimals, that's okay. Alright, fine. Sweet, huh? I think this is really cool. And you can do this on a napkin when you're out and about. So watch for those words. What do you know? Let's do ln3. You know that your function f of x is ln x. You know that you are looking for the tangent line at x equals e, because that e is about 2.7. That's very close to 3. Unleash the same procedure. Just find the tangent line, and once you have the equation for the tangent line, compute 3 in that linear equation. That's all it is. final. I'll show some more approximations now.
Yeah.
All right, let's take a look at this together. So we first find the tangent line. So I have the derivative of ln x is 1 over x. Slope m is the derivative computed at our pleasant value. Let's call it that way. So it's going to be 1 over e. Now we're going to compute the y value for this one. Y value is ln e, which is 1. So I have y equal mx plus b, which means 1 is equal to m is 1 over e times e plus b, from where we see that b is equal to 0 because e's cancel, and then you subtract 1 on both sides, b is 0. So we have our tangent line. Tangent line is given as y equals 1 over ex. That's what it is. Now, ln 3 is approximated by computing 1 over e times 3, which is 3 over e. Now, e is about 2.7, which I'm going to call 30 over 27. Cancel that by 3. Get 10 over 9, which is about 1.1. Go ahead, punch ln 3 in the calculator, see what you get. Anyone? 1.1? Wait, 1.0986, like this, right?
Yeah.
All right. We're not even a cent off yet. This is how awesome this technique is. We are computing the function values inside the tangent line, which is a simple calculation, rather than figuring out ln's, so on. You can try this to figure out how much is, I don't know, tangent of 2, right? You will find whatever, because 2 radians, right? You know that pi is about 3.14. So go figure out what value that revolves around a third of a pi or a sixth of a pi would work nicely with, let's say, number 2. So you go and you figure out how much is tangent of 2 using tangent line approximation. You can figure out any number this way, any function, any number, and it works pretty sweet. Now, what I want to do is one more theoretical piece here. So now we understand that the tangent line is the linear approximation. So I'm just going to write the formula. If you want to memorize more stuff, here it is. So linear approximation ln x is given as f of a plus f of a x minus a. So this is actually your tangent line done in one equation. So this is the entire process in one equation. Remember that we have to find the y value for the pleasant point. We have to find the derivative at the pleasant point, which was this one, and then this minus a is computation, the difference later that gives us the best approximation for x that we are looking for. So if you want to run either one of the previous two problems through this, you're going to get the same answers that we got, except it will be inline calculation rather than figuring out each step of the tangent line separately. So you can use either the formula, if you want to memorize the formula and use that, or you can just go through the entire tangent line procedure, figure out the tangent line, and then find, figure out the tangent line, and then you're done. That's the first part. Linear approximation, clearly called linear approximation because tangent line is linear line, y equals mx plus b, so this is called linear approximation. Now this particular, did I start the stream? Yes, I have, good. For the moment there. So what's happening next in your Calculus 3 class is upgrading this to tangent planes, because when you have a surface of some kind, let's say here is some kind of a shape, the linear approximation for this shape would be a plane that would touch, right, the shape at one point, just like a tangent line for the 2D graph. The equivalent for that in Calculus 3 would be tangent plane. Would be much easier to find, by the way, than this. But Calc 3 sounds like it's a scary course. It's actually easier than this stuff. So this will be upgraded later, and you're going to see this to be a part of a much infinitely long formula in Calc 2 called Taylor polynomial, and this will be just the first two terms of the infinite polynomial called Taylor polynomial. So you will see this again and again and again as you're going Calc 2 and Calc 3. It's going to be heavily used in differential equations as well. So this is the stuff that never goes away, this kind of approximation. The second part of this lecture is on differentials. We are going to now approximate from a different perspective. So linear approximation approximates the value. You see that what we got at the end is 1.1. So we approximated ln3, and we got approximately what it is, 1.1. And then you run it in calculator, good to go. Differentials are going to approximate the change. So they're not going to approximate the number exactly. They're going to approximate the change in y as you change x value from 3 to e. So it's going to be more like for these kind of problems, two-step procedure where you just figure out how much change happened between the y values, and then you have the easy y value, and then you add or subtract the change depending on the sign, and you get the value over there. So we're going to actually we can run the differentials against the same problems and check, but first we have to understand how differentials work, and differentials have attached to them a lot of these word problems, which are from engineering standpoint important, and I'll explain those to greater detail once we're there. So differentials. First, to derive differentials, we start with the precalculus y equals f of x. We know this from precalculus, just a notation for function. We differentiate both sides to get dy dx equals f prime of x. Nothing spectacular, right? And then what I do is I move dx to the other side, and I get dy is equal to f prime of x dx. This is what you want. Want to know, need to know, must know. I ran out of those words. Now I'll write it in blood. Differentials approximate the change in y. So they're not approximating number directly. They are approximating the change in y value as x goes from x1 to x2. So you see there is a change in x, right? You go from one value to another, from 15.8 to 16. There's a change there. So as you approximate the change in x, as there is a change in x, the change in y will happen. So that's what dy measures. It's also important to realize that what we call delta x, which is, let's say, x2 minus x1, that's the change in x. This delta x is actually the same as dx, where delta y, which is y2 minus y1, which is f of x2 minus f of x1, is not the same as dy, but it's close. And that's that approximation piece. So what I'm going to do is I'm going to compute dy, because dy, the differential, dy is easy to compute, and it's close to delta y. And that's where approximation comes from. So let's take a look immediately on the, what is 15.2 square root? I think it was, whatever. Square root of 15, I can come up with another example, but this one was good enough. So we have f of x is equal to square root of x, and we're going to work with 16, right? That's our new value. So what are we changing? We are changing 15.2 into 16, right? So delta x is equal to right, 15.2 minus 16, negative 0.8. So I have the delta x, and this is important piece of information, which is dx, is equal to negative 0.8. Now, we come up with a differential. dy is the derivative of the function times dx. What's the derivative of the function? 1 over 2 root x times dx. So now x is the easy one that we can compute, which is 1 over 2 times square root of 16 times negative 0.8. This is 1 over 8 times negative 0.8, which is negative 0.8 over 8, which is negative 0.1. So I'm going to write here that dy is negative 0.1. So how much is square root of 15? This is now 15.2. It is going to be square root of 16 minus 0.1. Because we are throwing in the change in y. And the change in y is negative 0.1. So I have 4 minus 0.1 is 3.9, which is exactly the same answer we had earlier. Except earlier, we calculated 3.9 directly. This time, we approximated the change. And then we either add or subtract that change from the y value over here. Does this make any sense? Right? So I'll go through this one more time. We have to find the square root of 15.2. We know that the function is square root of x. The easy number to compute close to 15.2 is 16. Right? So we are going to change 15.2 into 16. Which means that the change in x is 15.2 minus 16 equals to negative 0.8. So that's the change. And I have the change in x, delta x and dx is the same thing, negative 0.8. Differential formula is something that you must memorize. You saw it's very easy to derive. You find the derivative of the function times dx. We have dx as negative 0.8. Plug everything in. Easy value we are computing is 16. Compute, negative 0.1. So now we know that the change in y is approximated by 0.1, negative 0.1. So what do? We claim that the square root of 15.2, oh, I said equal, I was supposed to say approximate, I'll change that sign. It should be squiggle equal, right, it's approximated. And then what we have is the square root of 16 minus 0.1, 4 minus 0.1, 3.9. Good? Nice. Do we need to do one more of these with basic calculations, or switch to word problems right away? Word problems do more interesting stuff. Great. Thank you. Makes my day to some extent. All right. What are the engineering issues that we face as we are creating devices and building the planet? Well, why do we have that sound when you're on a train? Why is there that sound? Tick, 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 tick. Tick, 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 tick. Tick, 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 tick. Constantly. Tick, 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 tick. Tick, 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 tick. Two rails? Yeah, but couldn't they just do that a little bit better so there's no, like so they're smooth or something?
It's because when in the summer they expand, so that's the easy tiny.
Yes. So you will find this sound, tak 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 tak, more pronounced in the winter than in the summer. What happens is these rails are long. Let's say, I don't know, quarter mile, whatever. I don't know what the length is. So what happens is materials, when they're heated, they expand. So if you just put these rails next to each other, right, without leaving a gap, when they expand, they would have nowhere to expand, and they would start bending and they would break. And you can actually find images. I don't want to spend time now looking, but you can find very old images from old railways where these things were not taken in consideration, and in extreme heat, when they expand linearly, they run into each other, and then they just pop up, which derails trains. So now what you can do is you can calculate how much, there are formulas that are calculating exactly how much that expands, and because it expands a certain amount, they leave those gaps, and then they actually, in the summer, those gaps almost completely fill up, and in the winter, they are there. So you can, they're larger. So you can actually hear the sound in the winter much more than during the summer. Same thing happens with bridges. You drive over those very large bridges and you drive over a thing that looks like this, right? That's actually where the bridge is broken, right? And over the summer, that gap is closed. Over the winter, there is 1 or 2 inches apart, right? In there, 5 inches, whatever, but they look like that so you can drive over it. So long bridges, like the Verrazano Bridge and all the other bridges, will have those things. What else is there? So all of these are those expansions that happen due to heat. Design of electronics. Well, you should know what the CDs are, but Blu-ray discs. There you go. That's the new thing. Blu-ray. What happens when you put the Blu-ray inside the CD, inside a Blu-ray player? Yes. What shoots at it? Laser. And what lasers produce? Heat. Never had that one before. Okay, good to be the first. Good to be the first. So the laser will actually heat the disc, and what happens as the disc heats? Now, what do you think? How precise this stuff is? Very precise. So that expansion that we don't really see is going to impact a lot, because if you have a larger disk, right, and you have the linear rail with the head which contains the laser, moves linearly back and forth, it's going to read data off of the wrong spot, so you're going to have skipping and the movie is not going to look as good. So you have to incorporate that kind of design, right, into your equations as you move the head left and forth, right, back and forth to read the data off of the disk. And there are many other applications all over the place, you know, in sciences, in electronics, where these things are issue. Especially things that heat a lot. You want to do the same thing for pistons in the cars, right? So there's extreme heat there involved. There's a lot of friction as well. There's a lot of, you have engine oil, but still there is friction. It's hot. Cars are only about 27 to 30% efficient. Cars are actually one of the worst things that we actually have. Used to be the light bulb, but we don't use those light bulbs anymore. Those, what do you call those?
Fluorescent?
No, fluorescent. The incandescent, right? With the Wolfram coil inside like this. Those were actually, they used to be 2% light, 98% heat, right? That's how bad those lights are, and you really want to avoid them by all costs. And now even if they bump that up to 10%, it's still bad. And our cars, right? The energy that you get from the fuel, it's only 1/3 of, well, not even 1/3, right? It's about 27 to 30%, depending on which car you're talking about, efficient. That's the rest is heat, friction, right? Wasted energy, and that's so you know that, you know, when you buy a tank of gas, it's like at best 30% of that cost got you where you want to go, and 70% of the cost is wasted on heat that you can't actually utilize. This is why Tesla cars can be on the road soon enough at any point, right?
Once you drive the price down a bit.
Well, yeah, they will. Watch the documentaries on a Gigafactory. You'll see that the future is almost here. Can get rid of all of the other cars. So now let's take a look at very basic, obviously, and then maybe an advanced problem in terms of engineering. You have an ice cube which is melting. You have melting ice cube. The side went from, I don't know, 1 centimeter down to 0.9 centimeter. Approximate the change in volume. These are important questions for, I'll give you another example with this. You want to put less tire pressure in your tires in the winter or in the summer? Why? Yeah, due to heat, right? So you will be driving in the winter, you will be driving in the summer, so heat that is generated by the friction between the tire and the road should be approximately the same. But in the summer, you also have much warmer weather, say 50 degrees more, right? And if you have the equation, this is ideal gas, but it's good enough. You see that the pressure, the volume of the tire, and the temperature are related. So if you say that the volume of the tire stays unchanged and the temperature goes up, obviously pressure goes up, right? So lowering that pressure to compensate for a higher temperature. So there's a lot of applications of all of these things, and you have to worry. Life becomes very, very, very beautiful and easy when you incorporate all of the math you learn in it. You don't have to worry about picking up tire pieces down the road. Yeah, I know, no one does them. You just leave it. Someone else will pick it up. Are you done with the problem? I thought you'd be done by now. Volume is equal to side cubed, right? S changed from 1 to 0.9. So delta S is 0.9 minus 1, which is negative 0.1. The derivative of volume, which is dV, is equal to 3s squared ds. Now we know that the ds is negative 0.1. The side was 1 at some point, so change in volume. Oh, I forgot to change that sign, I remember now. There we go. So it's going to be 3 times 1 squared times negative 0.1, which is negative 0.3. And this is going to be centimeters cubed. That's the change. I don't know why I put centimeters cubed up. There we go. We also clearly see that, use a little bit of common sense, right? If ice cube is melting, then it's losing, right, stuff, so negative signs all over the place. We have the negative change on the side of the ice cube on each one, right? And then we have a loss on area, on volume, and surface area too. You can find any of these. So that's melting ice cube. You should be able to find applications of this for your chemistry and physics problems. Oh, they actually do have 58 ideal gas law. Pressure P, temperature T, and volume V of an ideal gas are related by PV equals nRT, where n is the number of moles of the gas and R is the universal gas constant. And then you can set those two to equal to 1, so you have your P equals to T cross V divided by V. You can normalized equation. And then they ask you, suppose that the change in temperature is this and change in, you can enjoy that. There's not that many problems. Let's find 2 more. So we have approximate the change in volume of the sphere. So we have a sphere, ball, right? And it says the radius is radius grows from 5 to 5.1 feet. Find the dV. Do we all remember the formula for volume of the sphere? Yeah, exactly. Good. That's all I heard on this end. And then someone said cube, so I was like, yeah, good enough. There's a cube there. Ready? It's like, I'm done. All right. We start with, well, delta R, which is actually dr. So that's 5.1 minus 5, which is 0.1. So we have that the dr is 0.1. Then we differentiate. So dv is equal to 4 pi r squared dr. We plug everything in. So 4 pi, r is going to be 5. And dr is 0.1. So that's 22 2 pi. Oh, that's what I said. Please pay attention. So 2500, 10 pi. That's 10 pi, obviously. Obviously. Good. What is this 10 pi? What is it? Let me see if any of the words I said earlier made sense. What is 10 pi exactly? Well, approximation of. Change in volume. Is there a way for us to figure out exact change in volume? Yes. How? Yes. Yes. So, this is the volume formula, right? We can compute this volume formula at 5 and at 5.1. The difference of those two is the true change in volume, right? But we want to avoid those calculations because this is much faster. And it's good enough for engineering purposes. So, you can go ahead, well, let's do it real quick. How about, you have your calculators. 5.1 here, and get a number, and then 5, and get a number. Subtract them. You better be around 10 pi, which is 31.4. So 5.1 cubed times pi times 4 divided by 3. Write that number down. Well, see, you can do one, you can do the other one, but that will be. Oh, and then I tax the other one. That's 60 cents off. 69. Is he not able to operate that heavy machinery? So you can always compute the true change, but that might be a bit more annoying to compute, longer. So we can approximate the change using the differential, and then so what is the, you had the number, 32?
32.048.
So 32.05, let's say. 32.05. And then the other, the number that we got is 10 pi, which is 31.4. Right? Look at that. That's 55 cents away. Right? So that's pretty damn good. You know? No, this is dV. This is dV because it's delta V that we don't know. So the true, let me just kill this line. Delta V is true change. So you will say that delta V is approximately 10 pi. Okay? So that's where the approximation comes in. So dV is the one that approximates delta V. So those are not the same. But delta X and dx, or delta R and dr, they are the same. And it all comes from the derivative. If you remember the 3.1, all the way back in 3.1, we said that H was the difference between A and B. H was B minus A. That's why dr, delta R, and dr are the same, because that's all one package. And that ends this lecture. We have first half, linear approximations, where we actually approximate the number, because we are computing the value that we must compute in the tangent line instead of the original function, and we are figuring out the value. With the differentials, we are approximating the change. So change in y, having the change in x. So that gives us all of this. So now, one more lecture. Let's restart the stream.